Hi all, welcome back to the section of finding eigenvectors of a particular matrix. And let's try a different problem. Here we are given a 3 by 3 matrix and is asked to find the eigenvalues and eigenvectors of the matrix. So as mentioned in the previous classes, we find the determinant of A minus lambda A equal to 0 and get the characteristic equation. And we have here, since it is an upper triangular matrix, you can see the determinant of A minus lambda is 2 minus lambda into 2 minus lambda into 3 minus lambda. So you can see that the eigenvalues are lambda equal to 2, again 2, and then 3. So corresponding to lambda equal to 2 and lambda equal to 3, we will be finding the eigenvectors. For that we will be creating A minus. Now we will consider when lambda is equal to 3. Similarly, we will find the matrix of A minus 3i and we will have this particular matrix. And this matrix into x, y, z will give you minus 1 into x plus y, 1 into y is equal to 0. So this will imply y is equal to x, and from the second row you have 0 into x plus negative y plus 0 is equal to 0, which means y is equal to 0. So if y is equal to 0 and y is equal to x, which will imply x is also equal to 0. So from the last equation you have 0 plus 0 plus 0 is equal to 0. You have no information. So what you can do is your x will be equal to 0 and your y will be equal to 0 and your z will be arbitrary. So your xyz would be equal to xyz will be equal to x is 0 and y is also 0. You can choose z to be arbitrary. Let me take it to be 1. So this is the second eigenvector. So for this particular matrix A, you are able to get only 2 eigenvectors. Okay, so there are cases where you are given a 3 by 3 matrix and you have 3 eigenvalues, but you can only get 2 distinct eigenvectors. Okay, there are cases also where you will be able to get only one eigenvector even if it is a 3 by 3 matrix. Okay, you can just do the problems. So I will just give you some problems as homework or some assignments, so you need to submit it in the site itself. Okay, lambda I into v is equal to 0. So let's consider the case when lambda equal to 2. At that time a minus 2i, we need a minus 2i and it's given by this particular matrix. And let x be equal to xyz, and we had v instead of v in this particular question. We took it to be the x. Okay, so we do a minus lambda I into x is equal to 0. At that time you can see when this is multiplied by x y z, we can see from the first equation y will be equal to 0. From the second equation you have no information, and from the third row when multiplying you will get 0 into x plus 0 into x plus 0 into y plus 1 into z is equal to 0, which will imply z is equal to 0. So since y and z are both equal to 0, what you can see is your vector x was equal to xy z, and since x is arbitrary, let us choose x to be 1, then y is 0, z is 0. So this is your eigenvector when lambda is equal to 2. So in case lambda equal to 2 was a repeated root and it was 2 times the root of the characteristic equation, but in this case you can find only one eigenvector. In the previous case we were able to find if the root was repeated 2 times, we were able to get 2 eigenvectors, but in this particular case we are only able to get one eigenvector. So even though the algebraic, I mean the multiplicity of 2 was 2, you will be, there are cases where you get only one eigenvector, and this question is an example of such case. Yeah, okay. Now moving on to the new topic, diagonalization or eigen decomposition. So diagonal, when you are given a 3 by 3 matrix, you can just make it similar to a particular diagonal matrix, and that process is called as the diagonalization or eigen decomposition. So diagonalization is a process by which a matrix A is reduced to its simplest form such that its eigenvalues remains the same and the both matrices are similar to each other. A matrix A is said to be diagonal. A matrix A is said to be diagonalizable if there exists an invertible matrix P, which is called as the model matrix, such that P inverse AP is equal to D, where D is a diagonal matrix and is called as the spectral matrix of A. So if you will be given a particular matrix A and this A is said to be diagonalizable if you are able to find an invertible matrix P, and that particular P is called as a model matrix, And also if you are able to get a diagonal matrix D, which is called the spectral matrix of A, so that P inverse A P can be written as a diagonal matrix, then you will be able to say that A is diagonalizable. It will be clear with the problems followed. So let's see a problem. And yeah, before that we'll see how we can form P. We need an invertible matrix P to write P inverse A P is equal to D. So that P is formed by, for a particular n by n matrix is diagonalizable if and only if if it is a n by n matrix, then you need to get n linearly independent eigenvectors, then only it will be diagonalizable. Okay, so if a square matrix A of order n has n linearly independent eigenvectors, then we can find a matrix P using eigenvectors. That is, if suppose A is a 3 by 3 matrix, I let x1, x2, x3 be the corresponding eigenvectors. Then what you do is you will form P by placing x1 as the first column, x2 as the second column, then x3 as the third column. Then you will be getting a particular P. And this matrix is the model matrix of A. And you will have the diagonal matrix D by, you will place this first column will be the eigenvector of a particular eigenvalue, and that eigenvalue will be written as the first entry, and then 0 is the entries of the first column. Then for the second column, for the second diagonal entry, you have the eigenvalue corresponding to the second eigenvector, and for the third diagonal entry you will be having the eigenvalue corresponding to the third eigenvector, and then you will have P and D, and then you will be able to write P inverse AP is equal to D. And the process of, you will be, if you have P, you know how to find P inverse. So the process of writing D as P inverse AP, or you can also write A can be written as, since P inverse AP is D, what is AP? Just multiply P on both sides. Okay, so you will be having AP is equal to PD, and from here you will be able to write A into multiply by P inverse on both sides, so A will be equal to PD P inverse. Okay, so you are able to write the given matrix A in A as in the form of PD P inverse. So writing A in this form is called, this process is called eigen decomposition. Okay, so we'll go into the problem now. Yeah, here we have the question: diagonalize the matrix. You are given a particular matrix and you are also asked to find what is A raised to 4. Okay, so what we do here is we are given with A and we first find the eigenvalues. So we have determinant of A minus lambda A equal to 0. Just as explained above, just find the eigen characteristic equation. So it is 3 minus lambda into lambda plus 1 into lambda minus 4 equal to 0. From this you have lambda is equal to 3, lambda is equal to -1, and lambda equal to 4. And here now when lambda is equal to -1, let's find what is A minus lambda I. So A minus lambda I is A minus -1 I, so it is A plus I. So you have A plus I is this one, and we'll be finding eigenvectors now. Okay, so in order to get the eigenvectors, what you do is just multiply by x, y, z, and you will be having, yeah, when multiplying the first row you have 2, let me write it here, let us take it to be x, y, z. So on multiplying you have 2x plus 6y plus z is equal to 0, and for the second one you have x plus 3y plus 0 is equal to 0, and you have 0 into x plus 0 into y plus 4z is equal to 0. From here you have z is equal to 0, and from here you have the equation x is equal to -3y, is it? And from this equation, while substituting x is equal to -3y here and z is equal to 0 here, what you have is -6y plus 6y plus 0 is equal to 0, which means 0 is equal to 0, is it? So this equation is consistent. Now what you can do is just form the matrix. So you have z is equal to 0 always, and you let it be y, and x is equal to -3y. Let's choose y to be equal to 1. So this can be equal to -3, 1 and 0. Okay, here our value we choose y to be -1, that's fine. We can choose it to be -1, and then your eigenvector would be -3 into -1, it would be 3, and here it would be -1, and here it is 0. So this is your eigenvector corresponding to the eigenvalue lambda equal to -1. Similarly, find the eigenvalues corresponding to the eigenvalue lambda equal to 3 So when lambda equal to 3, you have similarly find a minus 3i, and you will be getting the eigenvectors as for you will get the relation x is equal to y, and z is equal to negative 4y. Using that, just give the value to y, choose y to be 1, then y, since y is equal to x, you will be having x equal to 1, and since z is equal to negative 4y, z will be negative 4. So you will be having the next eigenvector to be 1 1 and negative 4. And when lambda equal to 4 also, in the similar way as explained before, just find the eigenvector. You will have the relation x is equal to 2y, z is equal to 0. So what you can do is, you can keep x to be 2y and then to be y and then 0, and choose y equal to 1. So x will be 2, y will be 1, and z is 0. So this is third eigenvector. Now you know how to form P, right? We'll just keep the first eigenvector, then second eigenvector, and then the third eigenvector. So in a similar way, this was our x1, 3, negative 1, 0, and this was our x2, 1, 1, negative 4, and this was our x3, that is 2, 1, 0. And 3, negative 1, 0 was the eigenvector corresponding to the eigenvalue negative 1. So you write negative 1 in the first diagonal entry, and your second column was corresponding to the eigenvalue 3. So you write the second diagonal entry to be 3, and here you have the eigenvector corresponding to the eigenvalue 4. So you have the third diagonal entry to be 4. Now we have P and D. Now our aim is to find P inverse. So you know what is P inverse? P inverse is given by 1 by determinant of P into adjoint of P. So we'll first find the determinant of P. So we have the matrix here. It would be easy for us to, yeah, you know how to find the determinant. 3 into determinant of this particular matrix minus 1 into, we'll be taking the determinant of negative 1, 1, 0, 0, plus 2 into, we'll be taking the determinant of this particular matrix negative 1, 1, 0, negative 4. Okay, and then simplify it, and we'll be getting determinant of P to be equal to 20, and since it's not equal to 0, this P is invertible. Now we need to find the adjoint of P. So hope you remember how to find the adjoint of P. What we do is, first we'll find C11, we'll find the cofactors of each entry. So in order to get C11, what we do is, we'll eliminate the first row and the first column, and then take the determinant of the rest of the matrix. So that will be the determinant of 1, 1, negative 4, 0, and then you have the value to be equal to 0 minus minus 4, which is 4, and then you will be finding C12. For C12, you will be eliminating first row and the second column. So you need to take the determinant of negative 1, 1, 0, 0. And since it's to find the cofactors, basically we have the formula Cij is equal to minus 1 whole raised to I plus j mij. Okay, so in fact this determinant of this particular matrix was equal to mij, and for the case of 1 1, minus 1 raised to 1 plus 1 is minus 1 raised to 2, and that is 1. So you need not have here negative 1, but in case of C12, you have minus 1 whole raised to 1 plus 2, that is negative 1 whole raised to 3, that is negative 1 itself. Okay, so you need this negative 1. And when coming to C13, you will eliminate first row and the third column, and you will be having the determinant of negative 1, 1, 0, negative 4. And now taking its determinant, it's 4. And here it will be minus 1 raised to 1 plus 3, that's positive. And now we'll go for C21. For C21, we'll be eliminating the second row and the first column. So we'll be finding the determinant of this matrix 1, 2, negative 4 and 0, then get the value, and also then add minus 1 whole raised to 2 plus 1 at the front, which is equal to minus 1 whole cube. So you need a negative in the front. Okay, so in similar way, just find all the values as shown here: C11, C12, C13, C21, C22, C23, and C31, C32, and C33. Then what you do is, you will get the form the cofactor matrix, which is given by, you can write the first entry is C11, which is 4, and the second entry is C12. C12 is 0, and the third entry is C13, which is 4, and here you have the entry C21. C21 is negative 8. Here you have C22, which is 0. Here you have C23, which is 12, and then you will be writing C31, which is negative 4, C32, negative 5, and C33, 4. So you have the cofactor matrix here. And then if you have the cofactor matrix, in order to find the adjoint, what you do is you will take the transpose of this particular matrix. So while taking the transpose, you have this to be your adjoint P, and then to get the P inverse, what you do is you divide it by the determinant. We have already found that determinant of P is equal to 20, so you just divide this particular matrix, each entry with 20, and then you have the P inverse. Now what we do is we'll just try to find what is PD P inverse. And PD in to find PD in P inverse, you just find what is PD, and then by finding PD you have this matrix just by matrix multiplication, and then PD P inverse is multiply this matrix with P inverse, which is 1 by 20 into this particular matrix. You can take 1 by 20 to outside, and just by matrix multiplication you will get this value to be this particular matrix, and then taking 20 to inside, you will be having first entry to be 1, second one to be 6, and this is 1. Here it would be 1, here it would be 2, here 0, 0, 0 and 3. So this was our initial matrix given. This is equal to our A, the matrix in the question. So in fact, you will be, if you are given a particular matrix A, if it is diagonalizable, you will be able to find one P, and by arranging the eigenvectors as the columns, and then we'll be able to find P inverse, and we'll be also getting diagonal matrix, and PD P inverse will be equal to A. So the process of writing A in terms of in this way, PD P inverse, is called eigen decomposition. Okay. Yeah. Now we were also asked to find what is A raised to 4, and we have the formula A raised to m is equal to, if A is equal to PD P inverse, A raised to m is equal to P D raised to m P inverse. So the advantage of this is we will be able to, since D is the diagonal matrix, it will be easy for us to find the powers of the diagonal matrix. It is more simple. Okay, so our A raised to 4 is equal to P D raised to 4 P inverse. Since our D is negative 1, 3, 4 on the diagonals, D raised to 4 will be the all these entries raised to the power of 4. Okay, so D raised to 4 is given by negative 1 whole raised to 4, which is 1, and 3 raised to 4, 3 raised to 4 is 81, and 4 raised to 4 is 256. So you have D raised to 4 here. Your A raised to 4 is now equal to, you will just multiply by P and P inverse on both the sides. Okay, you will multiply P on this side and P inverse on this side, and you will be able to get your A raised to 4. So first we will multiply by P D raised to 4. Just do the matrix multiplication and you will have the matrix, and then multiply by P inverse on this side. Okay, so multiplying by P inverse, you have the value of A raised to 4 is equal to this particular matrix. You can take 20 to the inside and you will be getting a simplified matrix, with the help of which you will be able to find A raised to 4 in a more simpler way. Okay, in fact, if you are trying to find A square directly, it would be a more complicated matrix, and then to A raised to 4 it would be again complicated. But since you know P and P inverse, this is an easy method to find the power of A raised to 4. Okay. Now let's try for a other matrix. You are given a particular matrix 2, 1, 0, 2. We are asked to find whether it's diagonalizable. A particular, as mentioned above, a particular n by n matrix is diagonalizable if and only if we are able to get n linearly independent eigenvectors. Since it's a 2 by 2 matrix, it should be it is diagonalizable if we are able to find two linearly independent eigenvectors. So by finding the characteristic value, by equating determinant of A minus lambda equal to 0, you have the value of lambda equal to 2. Okay, both the eigenvalues are 2, and now to find the eigenvector, what you do is A minus 2y into x. So you have A minus 2y to be this matrix, and multiplying it by xy, you have 0 into x plus y equal to 0, which implies y is equal to 0. So y is equal to 0 and x is arbitrary. So that particular eigenvector is, you can choose x to be 1 and y is 0. So this is your eigenvector. And A was a 2 by 2 matrix, and you have only one eigenvector. So is it diagonalizable? No. A matrix of order n is diagonalizable if and only if it has n linearly independent eigenvectors. Here the order of the matrix is equal to 2 and number of independent eigenvectors is equal to 1. Okay, since the eigenvector is less than the order of the matrix, then A is not diagonalizable. If A was diagonalizable, you will be able to find one more linearly independent eigenvector. Okay, so let's see in a similar way one more problem. We are asked to show that this particular matrix is not diagonalizable. So what you do is just find the eigenvalue by finding the determinant, and you have lambda equal to 1. And similarly, what we do is a minus I will find the value of a minus I into x is equal to 0. So when a minus I into x is equal to 0, what happens here is, here you will be having multiplying y is equal to 0, you will be getting, and from the second row you will be getting z is equal to 0. So x is, you can choose arbitrary. What happens here is, you are able to find only one linearly independent eigenvector, but the order of this matrix was a 3 by 3 matrix. Okay, so required eigenvectors was 3, but only the available eigenvector is 1, which implies A is not diagonalizable. You can practice these two problems. Okay, yeah, that's all for today's session.